Okay, so 2-4, we're going to define functions. Okay, and then we're going to, look to see if certain relations are functions. And then we'll start with objective B and do some domain and range. So we'll get through objectives A and B today. Tomorrow we'll be doing C and D. Okay, so looking at this objective A, we say that a function is a relation that pairs each element from the domain with exactly one element from the range. In other words, so a function is a relation that every input has only one output. So domain is input, range is output. So the input has only one output. Okay, so if I have this mapping diagram, I want to know if it's a function. So I'm looking at the domain, I'm looking at the inputs, and I want to make sure that for every domain value, there's only one range value. So for every input, there's only one output. So -2, output is 3, so that's okay. -1 has an output of 3, that's okay, but then it also has an output of 4. So because that -1 is paired with two different outputs, it is not a function. The 1 and 2 both going to the 5, that's okay. That's okay. So you can have the same output for different inputs, but you cannot have the same input for different outputs. So what you focus on are the x values, are your inputs, and if it repeats and gives you different outputs, then you know it's not a function. So you're focusing just here on the input. So this is our reason here, x equals -1 is mapped to two different numbers. So if I look at this table, I have an input and output. I see that 0 repeats, and it has different outputs. So I know that it is not a function because it's mapped to both 4 and -4. You could say the same thing for 1. You You could say it's not a function because 1 is mapped to -2 and 2. So it only takes one reason to not be a function. So you could use either one. You could say that it's not a function because the 0 repeats with different outputs. Or you could say it's not a function because the 1 repeats with different outputs. You could also just say a vague statement that it's not a function because you have multiple input values that have multiple output values. All right, I want to create a table, an input-output table. And input is always X, output is always Y. So when I make my table, I still have X is always my input, Y is always my output. But remember, to make a table, it's easier if it's X equals to plug in numbers for Y. Even though I'm plugging in numbers for Y, my input is still X. It's just to help me make my table. You sit right there in the front. That's the title. Okay, so we're going to plug in numbers for Y, just to help us make our table. Okay, -2 squared is +4. -1 squared is +1. Okay, 0 squared is 0. 1 squared is 1. 2 squared is 4. Then when you go to graph it, you still graph it like normal, x, y, so your ordered pairs are still x, comma, y. For -2, 1, -1, 0, 0, 1, 1, and 4, 2. So what you have is a horizontal parabola. So it looks like this. And I'm wanting to see if that's a function. So look at your table. Remember, read it input, output. So we're looking at the X column. Do I have repeated input? Yeah. So 4 and 4 repeat. Does it give you different outputs? Yes. So is this a function? No. So if you have 4, -2, and 4, -2, that's okay. But because it's 4, -2, and then 4, 2, it is not a function. You could say the same with 1 and -1 and 1, 1. So no, not a function. I'm going to say because 4 is mapped or paired. Sometimes your book will use paired with -2 and 2. Or I could have just said no, because there are some inputs that have multiple outputs. I could have been vague, or I could have said no because 1 is paired with -1 and 1. So it only takes one reason to not be a function. Any questions about that? Okay. All right, so the determine if they're functions. If it is not, give a reason. So take a minute to do this. Go ahead and do this on your own, and then we'll check back in. Okay, Corey, what do you have for A? Okay, good. Yes. It is a function. It did not say you had to state a reason, but the reason is because every input has only one output. Okay. Austin, what do you have for B? Okay. This one is not a function. Okay, because 0.5, so this one's not a function. Remember, we're looking at our x values. If it repeats, then it has to have the same output. So Maya, would you have, did you have it's not a function?
Yeah.
What was your reason?
Because 0.5 has different outputs for each two.
Okay. So she said because 0.5 has different outputs. That is perfectly fine. Okay. Lauren, what do you have for C?
It's not.
Okay. It is not. Jacob, what's your reason? Okay, because -1 has more than one output. You could have said also that -1 is paired with 7 and 9. You could have said something like that. You could have been specific, but this reason is perfectly fine too. Questions about that? Okay. So another way we can tell if something's a function if we're given a graph is the vertical line test. So a given graph is a function if and only if. So this IFF, that stands for if and only if. So it's a function if and only if every vertical line intersects the graph and at most one point. So vertical lines, no matter where you draw a vertical line, it can only go through the graph once. If it goes through more than once, then it is not a function. The if and only if, that means that it's the statement and its converse are true. So you could also say if every vertical line intersects the graph and at most one point, then it is a function. So you could go say it in reverse. That's kind of what if and only if means. So if I look at this piecewise function, so the graph is what's in blue, and then here's my vertical line. So this is what I'm using. So no matter where I draw a vertical line, okay, here it goes through once. Over here, just once. The only place really in question is this one right here, where it goes through both of those. But since this is an open circle, that means that is not a point. So it really only goes through the graph once, again. So this is a function because it only goes through once everywhere. That is an open circle, so that is not a point. Yes. So we're going to look at a couple more graphs. So this is a rational equation. So if I use this as my vertical line, okay, once, it looks like it would maybe go through more than once here, but the graph doesn't actually get vertical. It doesn't get straight up and down. Just, it gets really, really close, so it looks like it does. Same thing up here. So they still just go through one time. So this, yes, this one is a function. Okay, what about a circle? No, because it goes through twice. Circle is not a function. Okay, so if I look at this polynomial, what do we think? Function? Yes. Okay, so none of the lines went through more than once, so that means that it is a function. Okay, don't try to make these more difficult than they are. Okay, if you're given the ordered pairs, you're looking at the x values. They repeat with different outputs, then it's not a function. If you're given a graph, vertical lines go through once. Okay? All right, we're going to talk about domain. So here, domain and range, when you have a graph, you're just writing the boundaries. So domain is your x values, so you're looking left and right. Range is your y values, so you're looking bottom to top. You're looking up and down. It might be a little hard, maybe for some of you to see in the back, but there is a point here, an endpoint here, and there's an arrow here. So that makes a difference when we're doing domain and range. It doesn't tell me the notation, so I'm going to use interval notation. Domain is x, range is y. So if I look at domain first, I'm looking left to right. So is there a minimum x value? Yes, right here. Okay, so that is where x is -4. That's a closed circle, so that point is included in the graph. Okay, that's left. Now looking right, is there a maximum? No, there's an arrow here, so this goes continuously down, but also right. So positive infinity. All right, now we need to do the range. So the arrow makes you want to do the range like starting at the top to the bottom because the arrow is pointing down. But you always read your range. You always still have to go minimum to maximum. So you always start at the bottom, even though the arrow is pointing that way. You always read your range bottom to top. So is there a minimum y value? No. So we have negative infinity. Is there a maximum y value? Yes, at 5. Good. about that. So when you have a graph and you do domain and range, you're basically writing the boundaries. Okay, so you want to do your left and right, and then bottom to top. Okay, we're going to do domain of these special functions. We have done this already. We have already looked at domain and range, or domain of rationals and radicals. We're revisiting that again. Okay, we're also going to write it in interval and set notation. When I have a rational function, so that's when x is in the denominator, I have to look for my values that would give me a 0, because you cannot divide by 0, so I'm looking for those disclaimers. So in this case, x cannot equal what? -2. So now I just need to write that as a domain. So I have interval and set notation. All right, my interval notation. So I have -infinity up to -2, but I use a parentheses because I can't equal -2. And then I start back, so I do union -2 to positive infinity. So that tells me there's a pole at -2. X can be anything except -2. Using the parentheses tells me that I'm skipping the actual value of -2. All right, set notation. You have your braces, and then x such that, so use that vertical bar. X can be any real number, so x is an element of the reals, except -2. So x can't equal -2. Okay, for our next one, I only care about the denominator. So I don't care that there's an x minus 2 in the numerator. X could equal to, the numerator could be 0, that's fine. It's the denominator. So I need to know what x can't equal, so I'm going to have to factor this. I need it in factor form. I need to know what my disclaimers are, so I have to have it in factored form. So what's going to multiply to give me -12 and add to be -4? Okay, good. +2 and -6. Okay, so my disclaimers, I drew a line through that just so I had rewritten it. I didn't cancel that or anything like that. I just rewrote it as x plus 2, x minus 6. So my disclaimers are what? X can't equal -2 and 6. Okay. So now I got to write that as a domain. So I want to write the set notation first because set notation really doesn't change. It's always this x such that you have any real number, so x is an element of the reals, and then you insert your disclaimers. So x can't equal -2 or 6. Okay, so interval notation, basically describes the number line. It describes the places that would be shaded on the number line. So I want to write that out for you just so you can see it. Okay, so here's -2 and here's 6. So by saying x can't equal -2, that means there's a hole there. By saying x can't equal 6, there's also a hole there. Everything else is okay. So I shade everywhere else. So how many different places are shaded on this number line? 3. These two holes broke this number line into 3 sections. So you will have 3 intervals. We have x is an element from -infinity to -2. So we have that interval. And then we have the interval from -2 to 6. And then we have the interval from 6 to +infinity. So 3 intervals for this one. Okay. Connect them with your union sign. And we use all parentheses because of those holes at -2 and 6. Questions about that? So if you need to write out the number line, do that. It's not part of your answer, but it can help you write this domain. It can help you write your interval notation. All right, let's talk about radicals. Okay, again, I want to write this in set and interval notation. All right, so with radical functions, it's okay to be 0, so that's not what I am determining. The issues with radicals are they have to be positive, because you can't graph imaginary numbers on a standard coordinate plane. Okay, so I know what I want underneath needs to be positive, so I want to use the inequality. X minus 5 is greater than or equal to 0. So that's the technique that we're using, is we set that equal, greater than or equal to 0. It can be 0. Square root of 0 is 0. That still gives you a value. So that's why I have the equal to. Okay, so then x is greater than or equal to 5. So, again, let's look at that on a number line just to help us. Greater than or equal to 5 means I'm shaded here to the right of 5. And the equal to means I have a bracket. So how many intervals do I need here? Just one. There's only one place that's shaded. Okay, so I have only one interval there. And that's 5 to +infinity. Okay. Set notation, again, doesn't change very much. X can be any real number as long as x is greater than or equal to 5. Oh, sorry. I need another brace there. So the reason why we say this one's a little tricky is because it's a radical and a rational. Not only do you have a denominator, but you also have a radical in the denominator. So it's a combination of both. So the rational part tells me that x plus 3 can't equal 0. The radical part tells me that x plus 3 has to be greater than or equal to 0. So I want to combine those together. Okay? So I'm putting those together. So I'm going to say that x plus 3 is just greater than 0. I'm going to take off the equal to part because it can't equal 0 since it's now in the denominator. Do you see that? Okay, so that tells me then that x must be greater than -3. So for my interval notation, I have parentheses -3, and it's greater than, so positive infinity. And in my set notation, I have x such that x is an element of the reals, except x must be greater than -3. So any real number that's greater than -3. And we'll stop there. We will continue 2-4 tomorrow.